So now in this video, we come back to the 74HC02 integrated circuit. This one also has an N at the end, so it's probably slightly improved, but the main thing is 74HC02, 7400 series integrated circuit, high-speed CMOS version, and 02 means there are 4 NOR gates right there. So we got one up there that's wired up, and then one down here that's wired up. We'll come back to this one later. And it's not wired up as a NOR gate actually. The NOR gate is a universal logic gate. If you have enough of them, you can make any other logic gate that you want. Same with the NAND gate. I made videos earlier where I took the NAND gate and made other logic gates. We're going to do that with the NOR gate in this one. So the NOR gate, it's not an OR gate. It's an inverted OR gate. So an OR gate, if both inputs were low, then the output would be low. The blue LED would light up. But this is a NOR gate. So since they're both low, they're both to ground right now. So as long as I stay below halfway there with the trim pot, the output's high. So it's a NOR gate. So you can see we got ground on there, short lead the cathode, long lead the anode. Make sure you wire it the right way. 220 ohm resistor. So you know it's coming from the positive supply to light it up. If we put one or both of the inputs high, now we have a low output. You can see we got the jumper there to the positive supply, long lead anode, short lead cathode, higher value resistor, less current, but ultimately it's going to ground. That's the power pin right there. So we know that the output is low. As a universal logic gate, we're going to come back, or come down I mean, to this next one here. So you can see this jumper is to ground, low, 0 right there. And I tied both inputs together. So ultimately, that jumper is going to both inputs. That's as close as I can get. It'll go out of focus. But little jumper right there, connecting the two inputs together. And so they're getting the same input. They're both low, high output. Just like the NOR gate. And just like the NOR gate, if we go high, right now it's floating. It's picking up stray voltages, alternating current with the power supply of the house. Very weak signals, but enough to trigger it. That's why you don't leave inputs floating. And you can leave the outputs floating, but not the inputs with these integrated circuits. So in any case, there you can see high input, low output. And then since we only have technically one input now, we got one jumper going to both inputs, but the two inputs are getting the same signal. It's the same as one input right there. Low, high. We have an inverter right here. So we have a NOT gate or an inverter, whatever you want to call it. So the NOR gate is a NOT OR gate, and so it's an inverted OR gate. Here we have an inverter. So what we can do is go up to the output there, and we have our inverted OR gate, which we inverted again. So now we have an OR gate down here. Technically we have a NOR gate and an OR gate because our two inputs are up here now. And this red jumper is obnoxious, and so hopefully if I do that, it'll look better right there. So both inputs are low. Our OR gate is low. If one input goes high or the other, now our OR gate output goes high. Of course our NOR gate goes low. It's the opposite. But we're inverting our inverted OR gate, bringing us back to an OR gate right there. So now I have the power supply here. I bumped up the current. So right now you can see that's really it with the demonstration. NOR gate can make any other logic gate if you got enough of them. With two of them, we can make an OR gate. With just one of them, we can convert it from a NOR gate into an inverter. Pretty straightforward. So we are going to, we got the blue LED lit up down there. So let's bring the blue LED back. And there you can see with the blue and the red LED we got 13 milliamps of current. If I give a high input right there, we have two blue LEDs lit up. Current went way down. That's because blue LEDs are just naturally brighter than red LEDs. So let's bring that one to red. That one wasn't red before, but that one was red. Let's bring that back to red. Now we got twice the current of the red LEDs, and you can see it's a little more than 5 times as much current as the blue LEDs. So it went above the 20 milliamps. I'd like to keep it when I'm protecting LED circuits, but when the circuit needs more than 20 milliamps, of course, I have to bump it up. Every once in a while, I'll forget to do that, and I'll forget to raise the current, and you'll run into problems. And you can see CC right there. That means the power supply is providing all the current it can. And so the circuit has to make do with that current. Maybe it'll cause problems. So that's one of the troubleshooting things to look for, is typically you don't want to see CC right there. Whatever current you sent there should be the maximum. And if you see CC on there and you wired everything up, well, if you wired something wrong, you have a short circuit. You're getting more current than you expect. So if you wire everything right, then unless you made a wrong calculation or something, you should never see CC right there. So in any case, that's it for this video. Hope you enjoyed. Make sure you check out one of the other ones I posted on the screen. If you can donate, please do. That will help out the most, but just watching helps out a ton too. I appreciate that. I'll see you in the next video.